Hi, I'm Charlie Sullivan, and I'm delighted that so many of you are interested in coupled inductors, which is one of my favorite topics. We're going to talk about how they work for high current power delivery and some of the modeling and intuition behind them. Specifically, we'll talk about the concept of what coupled inductors are, why they're useful. We'll look at a simple intuitive model that lets you understand the basis of how they work and also gives you implications for how you get the full benefit of coupling. We'll also look at more complete models, both circuit models and formulas that give you equations like these and plots like these and predict exactly how they will perform. And we'll look at models to use in optimization, how to set up the optimization, and sample results from what you get from that. And we'll look at implementation options, discrete options, including lateral and vertical configurations, and on-die magnetics. But before we get into that, I want to tell you about the Power Management Integration Center. This webinar is brought to you by the Power Management Integration Center. It's a collaboration between UC San Diego and Dartmouth, and we work on next generation power electronics circuits, systems, and components, and innovations that support higher efficiency, smaller size, and reduced cost. And we think of that in three thrusts: discrete and integrated power electronic circuits, advanced passive components and integration, and power management systems, control, and applications. We have a bunch of industry members that I apologize, I'm hiding behind me. And this is part of the NSF IUCRC program. That's the Industry University Cooperative Research Centers program, which NSF has a lot of different kinds of center programs. This is the one that is most focused on industry, really designed to give the maximum benefits for the industry members. It's simplest, lowest cost model for industry university engagement. It's about half the cost or sometimes a lot less compared to a typical sponsored research agreement. And the member companies still are guiding the research. They're in the driver's seat deciding which research projects we pursue. The members get IP rights across all of the center research, and they get access to faculty and students, including, in some cases, NSF will pay for an internship of a grad student at your company. Our next meeting is in December 8th and 9th in San Diego, and we're open to new corporate members. So to get into the technology here, we're actually going to start without coupled inductors, just a multi-phase buck converter with, in this case, two phases that are switched out of phase. So when this pair of switches pulses high, this is held low and vice versa. And what that means is that the triangle currents in these two inductors, when one of them is rippling up, the other one's rippling down. And those ripple waveforms in the inductors add together where they're joined here to go to the output. And we get partial cancellation of the ripple current going out to the output, and thus reduced ripple voltage on that output capacitor or a smaller size capacitor for the same ripple voltage. That allows you that smaller capacitor, save a little money, save a little space. But one of the main reasons to be interested in this is that for the same ripple on the output, you can use smaller inductors. And in power delivery kinds of applications, you need fast response. And to get fast response, you need to have small inductors, reduce the energy storage there. It also saves you loss, cost, and size by using smaller inductors. And this has been around for maybe 30 years and is a popular approach, but it has some serious limitations, primarily that ripple cancellation only happens in the output there and a little bit on the input, but it doesn't happen through the inductors and the switches. So you get that high ripple current through there, high losses associated with that, need for peak current capability in the inductor, and that constrains how far you can go as far as achieving high efficiency, miniaturization, and low cost. So the coupling concept introduces some magnetic coupling between those two inductors. Depending on how you define the signs, it would be a negative value of mutual inductance. And that extends some of the ripple cancellation that you get in the output there back through these branches, through the phases, through the switches and the inductor. And that allows you to break some of that trade-off between how big is the ripple in this part of the circuit that's blue now, and how fast is your transient response. And so that's clearly beneficial in a way that we'd like. And the question is, how do we get that coupling in a physical structure? How much coupling can we do? And how much benefit do we get from that? So here are three approaches to how you could build a structure with two windings on it and have maybe some coupling. If you do that top one, you will get a little tiny bit of coupling, but that's basically a structure that lets you put two primarily independent windings on the same core. And that's sometimes useful for saving a little core material, saving a little space, but it's not going to give us substantial coupling. It isn't really useful here. The second one, we gap all the legs, we get a partial reduction in ripple through the whole thing. It's for an example set of numbers, we get 60% of the original ripple. And that sounds modest. It's actually pretty useful once you square the magnitude of the current to calculate the losses. So that's useful. But we can go to that bottom one. We're now maxing out the reduction that we can get. We can get a almost 60% reduction. In some cases, you can get more than 60%. If we go to, this is a two-phase version. If we go to a multi-phase version, we can get an even more dramatic reduction in ripple. And so that's substantially more beneficial. Again, if you square those numbers to get the loss implications, you might say, well, the loss is low enough here, but here you could go to smaller inductance values and get faster transient response while still getting that low ripple. Now, a lot of people look at that bottom one and wonder, can that possibly work? Because it's a closed core and we're going to want to run high currents through this, at least tens of amps, maybe even 100 amps through here. And generally you have a closed high permeability core and you run high currents through and you're going to saturate it. And here's one of the key advantages of coupling is the flux that's induced by each of those two windings is going in the opposite direction. So we have two fluxes that would be occurring going in opposite directions, but when you do superposition of those two, they cancel each other out as far as that full loop. And the only place where those fluxes add up is right through the center gap here. That's creating the leakage inductance. And so it's only the leakage inductance that sees the DC flux and not the magnetizing inductance, which means that we can max out that magnetizing inductance without fear of saturation. And so we can use that ungapped core with a high permeability material and max out the coupling. So that's the concept. And now we want to model it and understand what's really going on. So we want to have a circuit model for that structure. And there's a nice general result that anytime you put two windings on some structure, some magnetic structure, or just with the air core, you can always model that with a standard transformer model, which could be a pi model or a T model. In this case, it's the T model. And as long as we operate that linearly, we can use any of those models for any concept of how we want to use those two windings as coupled inductors, transformers, whatever. So there's our model ready to go straight out of the textbook. And what we're going to do with that model, which has two leakage inductances in the T model and one magnetizing inductance and an ideal transformer, and I should say that ideal transformer, we're going to use the same number of turns on both windings. And so that's going to be a one-to-one transformer. So that's pretty boring. We're going to take that structure and we're going to drop it into the circuit. And there we go. There's our full system model. We can put that into a circuit simulator, see what happens. And it will really accurately represent that ripple behavior that we can get out of that. So you can put it in a simulator, play around with it, tune up your intuition. But we don't want to just be simulation jockeys where we just run a simulation and we're surprised by the result every time. We want a way to think about this. And so one of the things we can do in thinking about it is we can say, well, we have an ungapped core that gives us a high magnetizing inductance. As we go to a higher and higher magnetizing inductance, that becomes like an open circuit. So for our base level understanding of the intended function of this circuit, we can just take that magnetizing inductance, assume it's very large, and a large impedance is an open circuit, so we just wipe that out, and we have this even simpler model. So here we have the ideal transformer, one-to-one, the two leakage inductances, and the switches, which are creating these pulsy waveforms here. And generally, this is used for low output voltage from a voltage more than twice the output voltage. So we're going to have waveforms that look something like this on the two VX nodes here. We're going to have waveforms like this that pulse, and they're 180 degrees out of phase, so they're pulsing alternately. And we know what inductors do. We know what the output filter does. The question is really, what do these Vy voltages do? What does the transformer do as far as synthesizing those Vy voltages that get applied to those leakage inductances and filtered to the output? And we could try to analyze that in terms of analyze the transformer function in terms of voltages or currents, but I think it's easier to think about it in terms of currents. It gives you more insight into what this whole thing is about. And so what does it do for currents? An ideal one-to-one transformer is going to force equal currents in both windings. It really only operates on the AC component, so equal AC currents in both windings. So I'm going to color those windings green to indicate those two. They're the same color code. They have the same current through them. And now, just by Kirchhoff's current law, those are in series with the inductors. So both of the inductors have equal AC currents between the two inductors. So if you have equal AC current through two inductors, the voltages across those inductors are the same. And the right end of those two are connected together to the same output voltage. So that means if the voltage across them is the same, then the voltages on this side, the Vys, are the same. So we don't need that subscript Vy1 and Vy2. We can just call it Vy. We have the same Vy on both of those. And now here's the part where I'm going to skip over some details. But if you think through, okay, what could those Vys be? The answer is that they have to be the average of the Vx voltages. So when we have one of those pulsing high and the other still at zero, well, the average of that is half of Vin. And either one of these pulses, we get Vy pulsing. So we get Vy pulsing to half of Vin at double the switching frequency. And so both of those are good for reducing the ripple in these inductors. We have lower voltage across them, and we have a higher frequency. So we're going to get some really good ripple reduction out of this effect. So that's the concept of how it works in steady state, how it allows you to have low ripple, even with these leakage inductances being quite small values. And you want those to be quite small values, both partly because you don't want to spend a lot of money in space and loss on high inductance values, but you also want them to be small for transient response. So how does the transient response work? Well, if you have a good control system, if you need to ramp up the output current, you are going to have both of your switches, both of your phase legs switching high at the same time. This averaging thing still works. So the average of two that are both at Vn is just Vn. So we end up with both of those Vy voltages right at Vn. The ideal transformer, when we're applying a common mode voltage across it, and it becomes transparent to that common mode voltage. So we can just delete that ideal transformer, and that's our model for the transient behavior. We just have those small leakages, and they're in parallel, allowing very fast response. So you can see we're getting everything we want out of this. We're controlling the ripple with little energy storage. We're getting blazingly fast transient response. That was just with two phases. Let's take this further and say, how could we do this for more phases? So we want the transformer to do the same current balancing function. That was what led to the behavior we want. And we also still want the DC flux cancellation, because that allowed us to accomplish this in a small structure with high magnetizing inductance, so it could approach that ideal of balancing the currents. So you go to a multi-winding transformer. A standard multi-winding transformer has multiple windings all around the same flux path. In practice, they're usually around the same post, but the key is they're linking the same flux, and so the voltages between them are the same or adjusted by the turns ratio. That's kind of the standard textbook transformer function. we didn't want to match the voltages. We wanted to match the currents. And so we need the dual of this function. And so we need the dual of the magnetic structure. We need all of the magnetic paths for each winding in parallel rather than series. Then the magnetic circuit model for this says all the MMFs have to be equal. That means with N's equal, it means all those currents have to be equal. And that's a standard old school, good old textbooks will have that described as a current balancing transformer option. Not nearly as common as this kind of multi-winding transformer, but a long-known technology for balancing currents. So that's kind of the basis that we want to use in constructing this coupled inductor. So let's see what happens when we do that for this circuit. Well, we have that same ladder structure, and we have windings on each rung of the ladder. And so there are our input voltages, and we combine them up to the output voltage. Same thing as with two windings, but we're now doing more of them. We could have a structure like this one where there's going to be some leakage, like it or not, and maybe that's enough, or maybe we have to add these center legs with a gap there or some other explicit leakage path to increase the leakage. Either way, the DC flux in all of those legs, I don't have three hands to point up for three places, but all those are going up, and so they're balanced, and we have no closed loop DC flux paths, and we don't get saturation. So we get that same saturation cancellation benefit, which is really key. If you look at some of the very early papers on this, people were experimenting with things like this one, where it really doesn't work. It doesn't give you the current balancing functionality because they're not in the right topology to do that. It doesn't give you the flux cancellation. You can't use a closed high permeability core and get strong coupling. So the key is the closed core enabled by flux cancellation and this structure where the windings are on the rungs of the ladder. And now it doesn't have to look just like that. You can do other geometries that are topologically equivalent. Here's the wagon wheel version, the coffee table version. You can have rings here, which, okay, technically isn't topologically equivalent, but magnetically it still has the same function. So it work in circuit-wise or magnetic circuit-wise, it is topologically equivalent. So now we have these structures that we can use for multi-phase coupling and get great performance, we think. But maybe we want a model to know how good is that performance. And those pictures look cool, but we'd like to intuitively understand what's going on. So we really want to do some more modeling. And I list there 4 different reasons that we might want to have a model. And I'm going to group that into 2 groups. So the first group is kind of a circuit-based thing. We're going to use, most of you are probably electrical engineers, so understanding function in terms of a circuit model probably makes sense. So we want that intuitive understanding. And we also want to rigorously quantify the benefit of coupling and predict performance. We also want to do magnetics design. We want to design what are we actually going to build for this, optimize that, and we may want that kind of more detailed magnetic design to go into a circuit simulation that will accurately simulate not just the concept of how this works, but the specific structure that you built. So we're first going to talk about the intuitive explanation kind of model and quantifying the benefit to predict performance. In terms of explaining the circuit function, okay, we want something simple and intuitive, and now I've thrown up something there that looks pretty complicated and messy. But it's really the same thing that we had before with the two-phase model. It's just that drawing the multiple winding transformer piece of the model is more complicated now. So the blue in there is the ideal transformer part that will balance all the currents, but then we also have the L mu that's next to the blue one. That's the magnetizing inductance, and the model structure we're using as an individual magnetizing inductance for each branch, for each phase. So that's kind of the proper full model for this. But for the intuitive explanation, we can still do the limit of what if the magnetizing inductance was very big, and then that whole funny structure on the left there just becomes a current balancing transformer. So I'm going to represent that just as a block. Drawing the current balancing transformer symbols is still a little messy. So that's just a block that's going to equalize all the AC currents in the limit that we have large magnetizing inductance. We actually get the same thing that we get the Vy that is between that blue box and the leakage inductance. Is that Vy is going to be the average of all of the Vx voltages. That allows us to get that full benefit of ripple cancellation throughout the whole circuit, so that whatever ripple cancellation we had at the output in that limit of high magnetizing inductance, we get that throughout the circuit. So that's our intuitive model. It also is a good circuit model for that level of abstraction. And we can use that model to develop equations that let us predict just how much ripple cancellation we get. Now actually backing up and saying we can have a finite magnetizing inductance there, not ignoring that and calculating more rigorously. And I'm going to draw pictures of the two-phase, but the equations here are for any number of phases. Number of phases is m in those equations. First thing is just to look at in the output where we have the full cancellation. That ripple cancellation in the output, I mean, full cancellation is like the maximum we could get, not all the ripple cancels and we have no ripple. That output ripple cancellation is independent of the coupling. All the coupling does is spread that cancellation we had in the output, spread it through the rest of the circuit. And regardless of what kind of magnetic structure we have here, we have kind of a fixed ripple in the output, assuming that we have the same inductance. One component of the ripple cancellation we get is just how good is that in the output? Because if it's not very good in the output, it doesn't really help to spread it through the rest of it. But usually it is very good in the output. So we want to have that quantified, and there's the formula for that. And that you can work out without any special magnetic stuff, just looking at the different normal buck converter waveforms and how they add up at the output. How much of that benefit do we get in this blue part when we increase coupling? And now here's a really critical point that people often get confused about and get to wrong conclusions because of it. As we increase the coupling, we have to think about what we're going to hold fixed. And a common way to think about it is to think about the degree of coupling in terms of a coupling coefficient, K, which is defined as the magnetizing inductance divided by the self-inductance. That's a ratio. So if you increase K, you haven't yet specified what you're going to hold fixed as you increase K. So different people might increase K and get different results because they were holding a different thing fixed. So we want to think about what makes sense to hold fixed. And what we're going to do is hold the transient response fixed, because that's a key specification for these kinds of applications. You need that transient response. And now how low can you get the ripple while achieving that transient response? We want to hold something fixed that relates to a performance characteristic, not just an arbitrary mathematical thing. So to hold the transient response fixed, we hold the leakage inductance fixed, because remember that the transformer function drops out, that becomes transparent for the transient. So holding the leakage inductance fixed, we now want to increase the coupling, and we're going to define our own coupling coefficient or coupling ratio beta, which we define as that ratio as a ratio with the leakage inductance on the bottom. By putting the thing that we're holding fixed on the bottom of the fraction, then it becomes clearer what's going on with that ratio. So that ratio, it's really normalized magnetizing inductance, normalized to that value we're holding fixed. So it's something much more physical. It's the actual magnetizing inductance that we're changing as we look at how much benefit we get from the coupling. So those are the two things that we're going to carry forward into the analysis: our capital gamma ripple reduction that we get just from the multiple phases, and beta, which is that ratio. And let's take a look at what we get from gamma before we try to combine them. So this is just uncoupled or coupled what happens in the output. We see that if we have a magic duty ratio that corresponds to 1 over the number of phases here, like with 4 phases, if we have a 25% duty ratio, we get perfect cancellation in the output. And that might make you think, oh, you need to operate at one of those nulls, but you don't really. Like if you look all the way at very low duty cycle with 4 phases, even when you're the furthest away from that null, you still get a factor of 4 reduction in ripple. So it's an added bonus if you're near one of those nulls, but it still works really well and gives you a benefit throughout that range. Now we want to also consider the strength of coupling and how much of this goes to the output. And I'm going to skip the algebra and just use the magic of PowerPoint that I can press a button and get a formula to appear. That's the formula that tells us the ripple reduction lowercase gamma throughout the whole phase leg, throughout the switches and windings, in terms of capital gamma and beta. So those combine in a simple way, and it ends up being kind of limited by whichever one is weaker. And we can put up a plot of that and see how that works. So that's a plot for beta equals 10. So we have the magnetizing inductance 10 times the leakage inductance. And we get, yeah, without looking carefully, those look like the same thing. It's just a little bit shifted up. And that means that when you get to that null, it's limited by beta. Or when you get to the large number of phases, it's limited by beta. But when you had something like, when you had a relatively modest reduction over here, you get pretty much that full reduction over here as well. And so as you get beta becoming large, you approach getting the full capital gamma reduction. As you get gamma approaching 0, then your reduction is limited by beta. So now we have a model, and we might want to go ahead and optimize this. We're going to, again, kind of drop back to 2-phase just to get a little practice and insight, and then I'll show you some optimization results for larger numbers of phases. We have this 2-winding structure that we're modeling with a transformer winding like that, and we have 2 degrees of freedom there. You can think of it as self-inductance and coupling coefficient, the off-diagonal and diagonal elements of an inductance matrix. You can think of it as magnetizing inductance L mu and leakage inductance LL. A naive design approach that you can find in the literature or in students' work when they first encounter this is to say, well, I know K from my circuit theory class, I'm going to find the optimal value of K. And they launch right into that without thinking about this question of, as you're adjusting K, what are you holding constant? Or maybe they say, well, if it's described by the self-inductance in K, let's just hold the self-inductance constant. As you increase the magnetizing inductance, you have less current through it, so you can actually use a higher self-inductance. And so if you make this choice of arbitrarily holding the self-inductance constant, which is a mistake, you'll see that a low K has no benefit. It's not coupled, it's just ordinary. A high K with self-inductance held constant, a high K has to be achieved by low leakage. And low leakage is bad. Too low is bad because that's the only thing limiting the ripple, and you'll just get high ripple. So you take a look at that and you say, oh, high K is bad, low K is bio, just pick something in the middle, and then you get a modest benefit and you think you've done all you can do. But that's not all you can do. If you fix the leakage inductance, because that determines the response speed, and it also determines the energy storage. As L mu becomes bigger and bigger, the amount of energy stored there goes down. And so the leakage inductance is where the energy is stored. That determines the physical size. We can fix that, and then we adjust L mu for best performance. We just want the highest L mu that's feasible. Maybe we have a material with a permeability of 2000 and no gap, and we get some L mu. Usually that's high enough to get a great benefit, and we don't have to go shopping for materials with permeability of 10,000 because that won't make much difference anymore. But within those feasibility constraints, we just want to use the biggest magnetizing inductance that's feasible. And so the optimization actually becomes simpler. We don't really even need a pencil and paper to do that. We just fix LL and max out magnetizing inductance. You might worry about this saturation thing again. The fixed self-inductance leads you to that. No real, I mean, you still have to design for saturation, but not a big deal there. This one looks scary if you're not experienced with how the flux cancellation works. Even once you've gotten over that hump and you understand how this works with the flux cancellation, you might think about it a little more and realize that, wait a minute, what if the DC current doesn't match perfectly? If this relies on cancellation, what if we have a few percent difference between those DC currents? Is this going to blow up? Because we don't tend to have materials, or low loss materials don't have permeability of 10,000 or 100,000 or anything, we don't get that super sensitive situation. If you just design with a typical low loss power material, just from experience, a typical number is that you can tolerate a 10% mismatch in those currents without having to do anything special. And if you have a good layout with the same DC resistance in each phase, if you have reasonably good tolerance on the on resistance of your FETs, and you have good precise timing, you are probably gonna stay within that 10% mismatch. If you don't have tight control over those DC currents and you're worried about, well, it's actually, my worst case is going to be 18% mismatch, you can add a small gap to those outer legs, and just the small gap will reduce the magnetizing inductance enough that you can get whatever mismatch tolerance you want. You can't just make it 100% mismatch, because then you'll be back to something that doesn't really have the full benefit. So you do want to have all of the phases active, and you do want them matched as well as you can, but they don't have to be ultra precise in that matching. A few days ago, I saw an interesting insight on what magnetizing inductance and what a core is for, from Jose Cobos. His question is why he's looking at doing high current transfer from a primary winding to a secondary winding and transferring a lot of energy between them at a high power rate. Yeah, optimizing for that energy transfer. That energy isn't going through the core. That's directly from one winding to the other? What's the core for? And his insight is that the core is there to avoid energy storage. And that actually applies to coupled inductors as well. It doesn't apply to all inductors, because a lot of inductors, you want to store energy and the core is there to help facilitate storing more energy. But with the coupled inductors, we want as little energy storage as we can get away with. If we just went for small air core inductors and no coupling, we'd have too much ripple. When that ripple's happening, we're storing energy that we don't want to store. The coupling enabled by a high permeability core actually reduces the needed energy storage. So we're also using that core to reduce energy storage. We have some formulas and circuit models to understand what the circuit operation is and what we want in terms of the parameters that come out of this structure. But when we actually go to design the structure to get that and predict what those values will be for some funny looking structure, we need to do some magnetic modeling. And the straightforward thing to do, if you have a structure like this ladder network and you want to model it, you can do a magnetic circuit model where you take each winding becomes an NI generator. Each leg has a reluctance corresponding to that leg, each of the rungs there, each of the risers, the pieces across the side there. Then this has one more reluctance for each phase, which is a leakage reluctance, which represents the flux that goes across one of those windows between those top and bottom bars. That's just transcribing that structure into a magnetic circuit model. Now, you could just go ahead and analyze, simulate that magnetic circuit model. We can also simplify it. If you look at the order of magnitude of the reluctances of the legs versus the leakage is a much higher reluctance. So exactly where that leakage is connected doesn't matter so much. It's like when you have wires and resistors, and the wires are much lower resistance. Those magnetic paths through the core are much lower reluctance. And then you look at all those leakages, they are in parallel once we consider the other connections wires. So we can represent all of those leakages in one central reluctance, RC, that's the net parallel leakage reluctance. And now we have a simplified magnetic circuit model. You don't need to simplify it, but then you can look at it and understand the different parameters that matter a little bit better. So taking that simplified magnetic circuit model and then using that in a circuit simulation, one thing we can do is we can directly implement that magnetic circuit model in a circuit simulator as if those were actually voltage sources and as if that flux was actually a current flow. The circuit simulator doesn't know that we're using that to represent flux. Or we can write circuit equations for this and put it in some programming language rather than using a circuit simulator per se. And then you couple this to, you can have the same simulation running your circuit simulation as well, coupled by having controlled sources. So this source would be N times the current that is measured through the winding. Okay, in that direction, it's straightforward. In the other direction, to get the voltage coupling out of this to go back to the circuit, you need the derivative of the flux through the winding, then multiplied by the number of turns. So you need to take a derivative somehow. You can make a little circuit to do that. So it's doable, but it's a little bit clumsy. So that's a perfectly viable option. We've done that many times. A little bit slicker approach is to do an inductance dual model. And there's a general rule that when you have a magnetic circuit and you look at what's the equivalent electric circuit, it's a dual, meaning that you interchange series with parallel as you move between the two. And also the reluctances, the units for reluctance are 1 over henries. So there's an inductance value that corresponds to 1 over the reluctance. And so we can consider an inductor that is 1 over, for each one of those reluctances, we consider an inductor that's 1 over that reluctance value. Here, all those main branches are in parallel. We put all of those in series here in one big loop. Within each branch, up there it has in series a generator and a reluctance. That becomes in parallel a winding that represents the coupling out to the circuit and has the turns ratio in it, and an inductor that corresponds to that reluctance. And this circuit will give you the behavior of that magnetic structure in the circuit domain. And it still gives you a connection. It's not just something that has the same terminal behavior. It gives you insight to what's going on physically in the circuit. The current through each of these inductors still corresponds to flux in that leg. The energy storage in this corresponds to the energy storage in the actual system. So you can see locally what's going on in the circuit, as well as just having something you can see locally what's going on in the magnetic structure, as well as having something you can simulate in a circuit simulator. And you don't need any funny business like derivative operators. This is just all normal things that would be directly available in any circuit simulator. So I did that for the simplified reluctance model. You may sometimes want to do a much more detailed reluctance model. Here's an example from this paper where there are individual reluctance elements representing each piece of the core and then also representing each path through the air. You might look at this and say, well, look, there are a bunch of series combinations, a bunch of parallel combinations. I'm going to simplify that immediately before I do anything else. But you might want to keep them separate in order to track what's going on with flux in the core that you can then use to calculate loss in the core in each of those elements of the core. And of course, there wouldn't be loss for the flux going through the air. So you want to keep those separate to understand that. So now that we have a way to model this, we may want to go ahead and do an optimization, a numerical optimization. Using those models, we have a way to calculate the circuit performance. And one comment that I want to make before we launch into that is when you do an optimization, there's not just going to be one thing that's optimal. There's an important step of thinking about what are your priorities? What objectives do you want to optimize for a particular circuit or for a particular business opportunity? With that said, here are some optimization results where we optimized for minimum loss. And so that was done by fixing the physical size of the inductor and fixing the response time. So we say we have a spec for response time. And we also say we're going to fix the MOSFETs that are used. We have a set of MOSFETs that's reasonably priced and reasonably good loss. So we fix that, fix those three things. And then we adjust the switching frequency, the geometry of the inductors. That affects the phase current ripple. All of those things are different for each design. We don't just choose the best frequency and then see what happens as we change the number of phases on the coupling, we re-optimize for each one of the bars shown on that chart. Those are, we're not comparing coupled and uncoupled for 4 phases, for example. We're saying, well, coupling's great. If you're going to do 4 phases, couple them all. If you're just going to do uncoupled, well, then just go to 1 phase. So that's the comparison that's laid out there. You might, yeah, there could be valid reasons to do other comparisons, but that's what this is. So the only one that's uncoupled there is the single phase version. All the other ones are coupled. And you can see that they're, as we couple more and more of them, the MOSFET losses just keep going down. And that's because with that fixed response time, we can keep reducing the ripple, and that keeps reducing the MOSFET losses. The total loss, including the inductor loss, is a little bit more complicated. At very low numbers of phases or the single phase uncoupled, we're just getting higher ripple through the phase, through the inductor. Higher ripple means higher loss. It's lower efficiency. So that's straightforward. But then we also have, as we go to very large numbers of phases, like 7, 8 phases, the loss gets worse there as well. And that's because with many small coupled inductors, many small inductors is unfavorable scaling for magnetics. If we weren't getting this coupling benefit, we'd be best off with just one large inductor, because that inductor is a larger scale and inductors get more efficient at larger scale. So in this example, it's around 3 to 5 phases that's optimum. That's pretty typical. You don't tend to see an optimization like this telling you you want much larger number of phases or many fewer phases. But it's not universal. That is specific to the parameters that were chosen in this optimization. I said before, you want to choose what performance parameters you're interested in. And so from this same optimization, but with things with the objectives and what's held fixed varied, here are 3 different examples of what you might want to choose and what you get for that. So the base case that we show over there is saying, well, we want to reduce loss and keep the response time, the cost of the FETs, we want to keep that the same. And we got a 25% reduction in loss, which is pretty nice. Maybe not all that exciting, honestly, but quite nice. If we said, well, our real target is we want to save money on the FETs, because that's an expensive part of this, we could have the same loss, the same response time, the same size of the inductor or the magnetic structure, and we could get a 36% reduction in the FET size. So that starts to look a little more substantial and directly connected to the bottom line. Another way to look at it is to say, well, what if we're okay with the cost of the FETs, we're okay with the loss, with the efficiency we're getting, but we really want to have faster response because the application's getting more demanding. We really need that fast response. Can we do that? Well, yeah, we can get a factor of 7 reduction in response time for the same loss and the same FETs. So there's not just, coupling is an improvement, and it doesn't just improve one thing. It allows us to improve overall and then take that benefit in the form we want, in what we really care about. Okay, so I want to look at a few implementation options here, and we can categorize those implementations a bunch of different ways. We can look at discrete implementations versus on-die implementations. We can look at low power, 70 watts versus this is a 70 kilowatt version. We can look at lateral current flow versus vertical current flow to package things different ways in a discrete implementation. There's also this new thing called a TLVR, and I want to talk a little bit about what is that and how does that compare to coupled inductors. And then we could do magnetic core or air core. Can you still get a benefit from coupling with air core? So I want to briefly talk about most of those. In the discrete implementations, these are kind of the early ones that were commercialized, looked like this. They're taking that ladder structure and they're just squishing it vertically, still taking that bottom bottom bar on the bottom, but the whole thing is squished down and squeezes out. You look at the latest versions of this that Analog Devices is offering, that ladder structure laid down flat with a winding around each rung, they're more faithful to that original concept. And that's an interesting question of why did we start out with stuff that was sort of weird and then eventually go to something more straightforward? So that's an interesting question, but maybe we can discuss in the comments. Another new implementation is doing vertical power delivery. And Princeton has done some great work on this. We've collaborated with them on the magnetics piece of it, but there's also a whole circuits piece of it that I won't get into with switched capacitor, hybrid switch capacitor, series parallel stuff, all that brings it down to 8 volts going into the final 4-phase coupled inductor buck converter, and then 3 of those combined to give you very high current at the output. But for the coupled inductor, one of the interesting things here, well, the very high current is one interesting thing. Another interesting thing is that we want to be able to put the power converter underneath the die and have vertical power delivery. So we keep the space on the sides of the board free for other things, and we don't have the extra power loss of sending that high current laterally on the board through long traces. So how do we make that coupled inductor? We want it to be thin. Well, vertical power delivery, that topology is kind of has one end of the winding at the bottom, another at the top, but we probably, for high current, we probably just want one turn. There's a lot of wasted space in that coffee table thing. So we can squish that down and compact it so we're using all of the space. And there above my head is one of the first implementations of that idea. But that first implementation was too tall. So there was a lot that we worked on together to refine that design and compact it, bring the height down all the way down to 2.5 millimeter in the most recent versions of that. And this is the result of that. The system's called the Lego system, and the original one is a 450 amp circuit with these 3 coupled inductors across in a very compact package. And then the newer one is the mini Lego. The current went down, but the size went down even more than the current. So it's actually double the power density going to that latest one all the way on the left there. So some fantastic work at that at Princeton. Kind of as an aside, this is just so cool, I had to mention it. Princeton has now done a version of this kind of thing that uses flying capacitor multi-level converters as the converter going into the coupled inductor, not for a VRM power delivery kind of application, but for an application where, for an optical communication system where they actually want a high frequency voltage waveform here, or current waveform through the diode. This thing has a 500 kilohertz switching frequency, but it can synthesize a clean 2.4 megahertz output sine wave. And that's combining the abilities of both the FCML and the coupled inductor in a really cool way. That was in a Compel paper that just came out, if you want to check that out. So I also promised to talk about the TLVR, and that's a new concept that's come out that is kind of the same overall circuit design. If you have a switch network, so that could just be in that blue box is just a buck converter. Then there's a little transformer there that is implemented like this. It's basically like an inductor with that thick silver colored winding, and then a little auxiliary winding as well. And that auxiliary winding runs between all the inductors in order to coordinate them and couple their behavior together. So it's kind of the same general concept with coupled inductors, but rather than being coupled by trying to clunkily place these big magnetic structures together, you just have this little wire going around coordinating things. The interesting thing is we developed this inductance dual model. We started using this inductance dual model before we'd ever heard of this TLVR. And you look at this inductance dual model versus that, and it's exactly the same thing. So that tells us, without even writing any circuit equations or running simulations, we know that the behavior of the coupled inductor and the behavior of the TLVR is exactly the same. So yeah, it gives you the same fast response with low ripple current that you can get from this, at least to the extent that you configure it with the same inductance values for the magnetizing inductance here and the self-inductance of those guys and the auxiliary inductor there, like the LC up there. So we can get a lot of the same advantages. So how would we decide between those implementations? They both give you at least the potential to have fast transient response with low ripple. The biggest thing you lose with the TLVR, though, is you don't get the flux cancellation. Remember, with this, we're able to get high magnetizing inductance with low energy storage because of that flux cancellation. In the TLVR, the coupling is only through an AC winding. And so that doesn't give you any of the DC flux cancellation. So here we can use zero gap. Those individual inductors in the TLVR have to each have a gap in them. And with that gap, in order to get the inductance you want for low ripple, they have to be physically larger volume. So the smallest magnetic volume for a given performance objective is the coupled inductors. The advantage of the TLVR is that you can have flexible layout. So if that was a little too complicated, here's the TLDR on the TLVR. It's the same great transient response and ripple characteristics, but without the size advantages that you get with coupled inductors. The advantage you do get is this flexible layout. So if that's what you're looking for, and that's more important than size and efficiency and cost and those kinds of things, then it's a good thing to consider. If you just want the best performance, coupled inductors is still the best. Can you do this with air core? It doesn't look like you can couple more than two phases, because if you just start putting multiple windings around the same central area, you get the wrong kind of coupling. So I've said for years that you can't do air core with more than two phases. I'm delighted that Minji Chen and his team at Princeton has proved me wrong on that. They've showed that you can couple more than two phases, but let's just talk about the two phases for the moment. If you put them side by side, you get a little benefit, but pretty weak coupling. So you probably want to put them on top of each other to get stronger coupling, except the kind of strong coupling you get there is reduction in leakage inductance. And that ends up with high ripple. So really what you need to do to get strong coupling is maybe not have them quite so close to each other and make them overall bigger to get big magnetizing inductance. Then that's physically larger than you'd ideally want. So you don't get the same kind of benefit. What you do get is you do get an improvement in the transient ripple trade-off. So that the TLDR on the air core is similar to the TLDR on the TLVR, which is you can improve the transient response ripple trade-off, but the size loss benefits are kind of minimal. And up above my head, there's the Princeton one with 4 phases. They've done even more than that. That's kind of more of a proof of principle, but actually proving that air cores can be commercially useful and viable, coupling 2 phases. There's the Intel Fiverr fully integrated voltage regulator, where it is in fact used to improve the transient response ripple trade-off, not to make it more compact than it would have been. It's compact by virtue of operating at very high frequencies. If you want to get stronger coupling than you can easily get with air core and want it to be compact, you may want on-die magnetic materials. And those are usually thin film materials, and that raises questions about the geometry and fabrication approaches. So those materials, on-die thin film materials, have some funny characteristics. One of them is that the really good ones are usually anisotropic, meaning that the hysteresis loop is different in different directions that you excite the magnetic material. So there's one direction, the blue one there, so-called hard axis, that's where you want to excite it. They also tend to have high permeability, which means you have to be careful about how you excite them to avoid saturation. And coupled inductors actually are a perfect match for solving those problems. So if you can't easily do it quite the same ladder core geometry, but what you can do is you can couple pairwise. So this is a 4-phase, an inductive structure for a 4-phase circuit, and it has 4 tunnels. Each tunnel has 2 windings in it, and that means that the current is going in opposite directions in each of those conductors going through one of those tunnels. That gives you the DC cancellation. So that means that green core can be very high permeability without concern about saturation. And the flux direction in there, there's no flux in the plane of the film. There's no flux going parallel to those windings. It's all going crossways, so you can make the good direction for the magnetic material crossways like that. We first designed something like that and fabricated prototypes working with Tyndall back in 2004. And that has now become more popular. Other people doing that, including Intel, including Columbia and Ferric. Apple commercialized that in one of their designs. You can see a large number of those pairwise coupled inductors here. And up there, you see a cross section of just one of those pairs of conductors. So it's exciting to see that concept being commercialized that way. So here are my general takeaways that apply beyond coupled inductors. And one of those is that it really matters what you hold fixed if you're optimizing something, particularly if you're optimizing one parameter. There's a bunch of other stuff that you're holding fixed. And if that's not what you want to hold fixed, you can get truly erroneous results. So for a coupled inductor, the magnetizing inductance and the leakage inductance each matter in terms of the physical implementation, in terms of the performance in the circuit. It's better to design thinking about those physical things that you want, what they do in the circuit, and just ignore K as such. We do it with this other ratio beta that's better aligned with thinking about those physical inductances. The other general conclusion is that if you optimize something well, then you can use that optimization process not just to make it generically better, but to very specifically get what you want out of it. And that means that if you make an improvement, like you have a better material for something, you have a better structure for something, and maybe that better material improves one parameter, it reduces loss, but you really wanted to reduce size, you can do that optimization with the right objectives and use any improvement to get what you really want out of it. So don't ignore improvements that seem like they improve different things than what you're after, because you can rebalance things in the optimization and get what you want for commercial or research objectives. So here are some more specific conclusions about coupled inductors. One is that this inductance dual model can be a useful way to model coupled inductor structures for this application and others. Another conclusion is that you can calculate the ripple reduction and understand that as being a combination of these two parameters, capital gamma and beta, and they combine in this pretty simple formula. So you can see how both of those factors come together to give you the ripple performance. The TLVR can duplicate the ripple reduction and transient response of a coupled inductor, but it loses the DC flux cancellation benefits. So the magnetics end up bigger and lossier. So you only want to use that if you want the locational flexibility, coupling with a little wire rather than coupling with magnetics adjacent to each other. There are implementation options, very high performance ones for lateral current delivery, for vertical power delivery. Coupled inductors are also an effective way to use high permeability anisotropic thin film magnetic materials for on-die magnetics. Looking forward, we do have a project at PMIC on coupled inductors for high current power delivery. I can't talk about that publicly yet, but preliminary results will be reported to the member companies of the Power Management Integration Center in December at our Industry Advisory Board meeting in San Diego. If your company is not yet a member but would be interested in that, contact us, and there'll be a link below to learn more about the center. And that's just one of the 6 ongoing PMIC-sponsored research projects, and there are dozens going back over the last 5 or 6 years. Thank you for viewing this presentation, and we will be answering questions in the comments below, so please take a look at that.